Welcome to Eureka Math. I'm Mr. Shankel. I'm going to be helping you today with Module 1, Lesson 10. Let's get started. All right, exercise 1 gives us the speed of light is 3 million meters per second. The sun is approximately 1.5 times 10 to the 11th meters from Earth. How many seconds does it take for sunlight to reach Earth? Well, I'm going to start with the distance the sun is from the Earth. That's 1.5 times 10 to the 11th power. And then I'm going to divide that by the speed of light, which is this 3 million meters per second. But I want to write that as scientific notation. So it's 3 times 10 to the, well, I've got 3, 6, 8. So 3 times 10 to the 8th power. And then I can divide 1.5 divided by 3 gives us 0.5 times 10 to the, well, since we're dividing exponents with the same base, I can subtract these exponents. So 11 minus 8 is 3. So that's 0.5 times 10 to the third. And then you should be able to recognize that we are not in scientific notation. I need a leading digit before the decimal, between 1 and 9. So this is going to be 5 times 10, and then look, since we started with a 0.5 and we're going to change it to something bigger, 5 is bigger than 0.5, then my exponent has to get lower. So that's going to be 10 to the second power, and that means that it takes 500 seconds. 500 seconds for light to reach Earth from the sun. All right, exercise 3. Exercise 2, we lost a slide there for a second. Okay, exercise 2, the mass of the moon is about 7.3 times 10 to the 22nd kilograms. It would take approximately 26 million moons to equal the mass of the sun, determine the mass of the sun. So we're going to multiply the mass of the moon times the number of moons that it would take to equal the mass of the sun. So we're going to take the 7.3 times 10 to the 22nd power, and we're going to multiply that by the mass of the number of moons, and I'm going to write that in scientific notation, 2.6 times 10 to the, well, I've got 3, 6, 7. So this is 10 to the 7th power. All right, and then we're going to go ahead and multiply. 2.6 times 7.3 is 18.98 times 10 to the, well, now since we're multiplying exponents with the same base, I can add these exponents. So that is 10 to the 29th power. And again, we are not in scientific notation, so I'm going to move my decimal back. So I get 1.898 times 10 to the, and our exponent now, we had an 18, now we changed it to a 1, so that got smaller. That means our exponent has to make up for that by getting bigger, so that has to be a 30. So it's 1.898 times 10 to the 30th kilograms is the mass of the sun. All right, now we're on to exercise 3. The mass of the Earth is 5.9 times 10 to the 24th kilograms. The mass of Pluto is a lot of kilograms. Compared to Pluto, how much greater is Earth's mass than Pluto's mass? Well, this is going to be a subtraction problem, so I'm going to take 5.9 times 10 to the 24th, and I'm going to subtract Pluto. Well, Pluto is going to be 1.3 times 10 to something, and we've got to figure that out. 3, 6, 9, 12, 15, 18, 21, 22, 10 to the 22nd power. So there's Pluto. And now we need to subtract. But remember, our exponents need to be the same in order to add or subtract. So I'm going to change my Earth. I'm going to change my Earth into to the 22nd power. So I'm going to change this to 10 to the 22nd power, and realize that that has gone down, so my number has to be bigger by 2. So this is going to be 5,900 times 10 to the 22nd power. And then I can subtract my 1.3 times 10 to the 22nd power. So now that I have my exponents the same, I can do my subtraction. And I just noticed I made a mistake. I moved my decimal 2 places, which means I fill in 1 0. So that should be 590, not 5,900. Let me see if I can erase. 590 times 10 to the 22nd power. There we go. And then we can go ahead and subtract. 590 minus 1.3 would be 589.7. 589.7. No, 588.7. 588.7. And then I can just use my 10 to the 22nd power. So 588.7 now is not in scientific notation, so I need to move my decimal back 2 places, and this is going to be 5.887 times 10 to the 22nd power. Not 22nd power, because I moved it back 2, making it smaller, which means my exponent has to get bigger. 5.887 to the 24th power. And that is how much greater Earth's mass is compared to Pluto. Kilograms. All right, be careful, right? When you're moving these around and you're changing to scientific notation. I almost made this mistake here. I forgot to bump my exponent up. So when one changes, then the other one has to adjust accordingly, okay? All right. Exercise 4, using the information in exercise 2 and 3, find the combined mass of the Moon, Earth, and Pluto. Well, let me get those for you. Okay, so here we are with the mass of the Moon, the Earth, and Pluto, and I want to add all of these together, which means that all of my exponents are going to need to be the same thing. So this Earth I'm going to have to change. So I want that to be a 22. So this is going to be, times 10 to the 22nd power. Since that got smaller, my number was going to get bigger by 2 place values. So this is 590 times 10 to the 22nd. So now I have 10 to the 22nd for the Moon, I have 10 to the 22nd for Earth, and I have 10 to the 22nd for Pluto. And now I can add all of these together. So 590, I'm going to add, let me box these up. I'm going to add this 590 and the 7.3 from the Moon and the 1.3 from Pluto. So the Moon and Pluto is going to be 8.6. So I get a total of 598.6 times 10 to the 22nd power. And then, of course, I need to change back into scientific notation. So 2 places to the left gives me 5.986 times 10 to the, well, I moved 2 places and made it smaller, so this has to be bigger to compensate, and that is 10 to the 24th power. So 5.986 times 10 to the 24th power kilograms is the combined mass of the Moon, Earth, and Pluto. All right, and then lastly, how many combined Moon, Earth, and Pluto masses are needed to equal the mass of the Sun? Okay, so I've brought over the mass of the Sun. The Sun is the one on the top. And then the combined of the Earth, Moon, and Pluto combined And in order to find out how many of these we would need, how many Earth, Moon, and Pluto masses we would need to equal the mass of the Sun, we're going to do division. And so I'm going to do some division here. So we're going to take this 1.898 divided by 5.986. And when we do that, that gives us a 0.32 approximately. So we're going to go with 0.32. And then since I'm dividing exponents with the same base, I can subtract the exponents. So this is times 10 to the 6th power. So 0.32 now is not in scientific notation, so I'm going to move my decimal. And I have a smaller number. It's now going to be a little bit bigger, 3.2. So that means my exponent has to adjust accordingly, and that's going to be 3.2 times 10 to the 5th power, since I only moved one space over, one decimal place. So 3.2 times 10 to the 5th combined masses of Earth and Pluto it would take to equal the Sun. I don't need kilograms there. A lot. You can see how enormous the Sun is. Okay, that is lesson 10. I hope that helps. See you again next time.